Okay, so let me see what you know. Oh, where did I put that?
Is this still 7.1 or are we moving on?
I'll let you decide.
I think we're moving on.
You do.
I think we're still.
But there's one question I do have. On.
Yeah, exactly.
You're gonna tell me if you know how to do this one. I got a 2x minus 1 on top. Bad marker, we'll put you over here. Let's grab one of mine. 2x minus 1 on top, x squared minus 6x plus 13 on the bottom. And I'm asking you to integrate it. 2x minus 1 on top. And so I want you to have a thought process. I know that's probably asking a lot.
Are we doing inverse quotient?
Well, that has something I took the derivative of, ended up like that, so it could be. So normally when you see a fraction, what's the first thing you try? It is simplified. See if the top has anything to do with the derivative of the bottom. So set u to be the bottom and let's see how close we are. Right, we always try the easy stuff first. Does a u du substitution work? So when I take the derivative of the bottom, we get 2x minus 6. Oh, doggone it, I don't have a 2x minus 6. I have a 2x minus 1. I could also look to see if the bottom factors and if there's a factor of 2x minus 1 in there, but clearly there's not. So now I need you to become resourceful. Gave you some things to throw in your bag of integration tricks. You got anything in there that you can pull out and suggest?
Complete the square.
We can try to complete the square. What about the 2x minus 1? How's that going to help us?
Yeah, that doesn't escape our trap, right?
I'm going to complete the square eventually. What if I wanted to put a 6 where that minus 1 is? How can I legally do that in every state except Arkansas?
Subtract 5.
Okay, I want to subtract 5 and then add 5. So that's what I'm going to do first, so that at least I've got part of the integral that I can do. I'll worry about the add 5 later. Okay, so I'm going to put what I need right there. I need a minus 6 there, so I need 5 more, and then I got to take it back out. So I'm going to put that together and make one integral out of it. I'm going to make another integral out of that one. So I have a 2x minus 6 over x squared minus 6x plus 13. That one we can do now with that. The plus 5, I'm going to use your suggestion about completing the square. See, we get to use 2 of our tricks in our bag of tricks. This problem is like a buy one, get one free.
What a steal.
What a steal. We get to do our adding 0 and we get to do our completing the square. And so the first one is going to be our u du substitution. I've got that set up just right. So that's a 1 over u du. We finish it off because we're playing that partial credit game. We've got half the problem right here. Okay, so that's the first integral. And then the second one, the suggestion was to complete the square, and I think that's an awesome suggestion. So let me give you a second here and see if you remember how to complete the square on that. Move the 13 out of the way a bit, half the middle term squared, add it, subtract it. Sir,
You want,
you ready to do it? Everybody done?
Yeah.
Okay. Now let me complete the square up here. Look how tall I am today. What number am I adding?
9.
And then I gotta take a 9 out. And then how does this right here factor?
-3.
X minus 3 all squared, that adds to 4. So we can write that second integral as 5 times x minus 3 all squared plus 4. Well, did completing the square give you something that you recognize that you know how to integrate?
If you squared plus a.
I've got a u squared plus a squared, right? So we use another change of variable. I've already used a u, let me use a w. W is x minus 3, dw is dx. And so I gotta go way over there. And so I still have my natural log of whatever, let's tally that along. And then my W substitution gives me 5 W squared plus 4 DW. What's this integral gonna give me?
That'll be 1 over
And
2.
inverse tangent.
It's an inverse tangent of W over
2.
2 with a 1/2 out in front.
And then u over, or w over 2 as well.
So the 5 is just a constant. Now we have an inverse tangent of W over 2 with a 1/2 out front. And then replace the W with our x minus 3 squared plus 4, and we're done.
W is just x minus 3.
Oops, you're right. Now there's too many parentheses, but such and such.
You can never have enough parentheses.
Parentheses are free, just like,
Sorry. So what you did was you divided by 4 to make the 4 1, right? And then. you
I just
divided-
used the general version of that formula. Remember, we spent some time making them all general versions. Let me write the 3 formulas up here. Is that what you were-
Down behind you, you want some?
An eraser.
Oh, eraser, that's a good question. Did you use a rag? Finger?
I did, but who took it?
Here's the
eraser.
We had these general forms. The one I'm using here is 1 over u squared plus a squared
1 over
is 1 over a arctangent or inverse tangent of u over a plus c. If I have square root signs, and if the u is behind the minus sign, that's an inverse sine of u over a. Remember, this one does not have a 1 over a out front. And if I have a variable outside and the variable squared in front of the minus sign, that's an inverse secant of u over a. This one does have a 1 over a out front. So those are the general versions of the inverse trig integrals where we didn't have a 1.
then would, if we did like, if we like an arc cotangent.
Our cotangent just has a minus
Negative.
sign here. Our cosine has a minus there, so we don't need them.
The answers would just all come out to be negative, right?
Right. Okay,
So you can just replace that 1 with like a 5.
right. I factor the 5 out.
Oh,
Right.
okay.
So I tack it on in the end, just like with derivatives. If there's a constant that's you can pull out, you can pull it out. Okay? All right, that was just our stretching exercises. Now your muscles are somewhat limber. Here's another one. Still don't want to pull anything, so we can keep stretching you out. Let's under here, put 9x minus x squared. Clearly not a UDU integral, and it's not quite this one because I don't have a constant in front of the variable squared. I got a 9x instead of a 9x, instead of a 9 by itself.
Oh wait, no, I'm gonna do it.
Can you complete the square? It's kind of weird though, the negative x
You
squared.
can complete the square. So see if you can complete the square without blowing any signs anywhere. Try to complete the square on that. And half of 9 is 9 halves. That's it.
Actually, I needed that.
You needed that? 9 halves squared is 81 fourths.
So whenever we do that, we pull out the, so it would end up, would it end up just canceling itself?
What do you mean?
Because like we have to pull it out, right? Or do we just get to add that?
Erase something squared and then under the radical.
I'm lost.
Me too.
Ignore the radical for now. Just let's complete the square on this. There, well, here's our middle term. Half of 9 is 9 halves. 9 halves squared is 81 fourths. So add it in, take it out. Okay? When you factor this,
You can.
should factor is a perfect square. And then I'd need a minus x there to get the minus x squared. I know what I multiplied together to get me that, so that should be a 9 halves right here. Is that going to give us the right middle term if we were to multiply that out?
You have to take the negative out first, right?
Have to, you can,
Well, that makes it easier.
does.
Yeah, a lot easier.
I don't like to make things easier.
But then it ends
Yeah.
up weird, because then you end up with a -1 in under the radical.
Like that?
Isn't minus x times minus x just x squared, not minus x squared?
So you're right. So better take the -1 out. I said, be careful not to blow the sign, and what did I do? I blew the sign. I just did that to make you feel better, because I don't want you to feel bad when you blow signs. So I agree. I think I'm gonna take the minus sign out first. I'm gonna write that as -1 times x squared minus 9x. And then I'm gonna complete the square in there. So now I'm gonna get my 9 halves squared right here is 81 over 4. And I'm gonna take it out right there.
And you can just take out that 81 over 4, right?
I will after I put this in.
Yeah.
And so I got a -1 times this part here factors
So that's x minus
as
9
x minus 3 halves squared minus
halves. Isn't it
81
9
over
halves?
4.
Yeah. Yes.
9.
Okay, that was a little.
Do I get partial credit?
Yes.
I don't need it. I have my degree. Okay, now I'm gonna put that minus sign back in, which makes the 81 over 4 positive, so I'm gonna write in front, and then the x minus 9 halves squared in the back. So I have 81 over 4 minus x minus 9 halves squared. That's gonna go underneath the radical sign. Did I lose anybody on that? Good.
I think I'm still here.
Okay? All right, so I'm gonna put it back under the radical sign, and now here's the problem we've got. I have 81 over 4 here. minus x minus 9 halves all squared right there. Does that remind you of any of the formulas that I've written next to it? Which one?
A squared minus square root of a squared.
I've got a squared minus u squared, the u is the variable. So let's go ahead and make the formal substitution, what we call that u. Take u to be x minus 9 halves. That leaves me du as dx. So this is simply the integral of 1 over 81 over 4 minus u squared du. So the a here is 9 halves. I don't have a 1 over a for an arc sine, I just have an arc sine. In this case, it's going to be u over a plus c. Dividing by 9 halves is the same as multiplying by 2/9. And my u is x minus 9 halves. You can send the 2 through the parentheses and then you don't have to worry about fractions in there. Is that okay?
I have a question.
Yes.
Is there like rules for imaginary numbers in this?
Is there rules for imaginary numbers? What do you mean?
Like, what's the integral of an imaginary number?
Then you have to figure out what an integral means, right? Remember that when we devise integrals, we're thinking of things this way. Imaginary things are like our polar things. So you'll have to take a course in complex analysis in order to figure out how to integrate the complex.
Because I was like, oh, you can just take the negative out of the integral, and then I was like, wait, no, you gotta have the square root. And then I was like, oh, wait, no, that
It's
negative.
a whole different connotation. All this calculus is done differently in the complex plane.
Sounds fun.
It's fun. You think so? Okay, so we still have to practice the integrals that we know how to do and go a little bit further each time. And not just your ordinary UDU substitution, not just your ordinary complete the square. We got to mess with fractions and minus signs in the wrong spot and things like that. We got to keep honing our skills and getting better at the things we know how to do. So today I'm going to go through and show you how to use that integration by parts formula, how to integrate products. We can integrate products if they have the form where one of the factors has its derivative as the other factor. That's an ordinary UDU substitution. That's what UDU means. One function u has its derivative du as the other factor. If a product doesn't have this form, but has the form that I put up here on the board the other day, one factor that you can take the derivative of, one factor that you can take the antiderivative of, from the product rule, we can figure out how to integrate that type. That type of problem typically looks like one of our trig functions times an x, or x times e to the x, or think of some of the functions that we don't know how to integrate. A natural log of x. We know how to take its derivative, but we don't know how to integrate it. We'll be able to use this integration by parts to integrate a natural log of x. I know integrals that yield inverse trig functions, but if my integrand itself is an inverse trig function, I'm going to use integration by parts to find what the integral of something like that is. So here's our integration by parts formula. Thank you. All right, let me roll this off. So maybe I'll go through and derive the formula again. And it came from the product rule. So if both u and v are functions of x, this is section 7.2, integration by parts. The product rule says that to take the derivative with respect to x of the product of two functions. You hold one, multiply by the derivative of the other, plus the other times the derivative of the first. First times the derivative of the second plus the second times the derivative of the first. And then in deriving the integration by parts formula, what we do next is we integrate both sides with respect to x. So I'm going to integrate that with respect to x. Should have left more room. Let me scoot you over. So what did I, oops, get back here now, put you in red. I said first times the derivative of the second. I'm going to go ahead and integrate that with respect to x. Plus, now my integral sign, second times the derivative of the first.
You write dx.
I'm integrating with respect to the variable x. So this pairs with that pairs with that. I'm going to go through there and integrate each term with respect to x. But the left-hand side, we're integrating with respect to x something whose derivative appears there. And the integral of a derivative just gives you the stuff inside. U times v is equal to u times v prime times dx plus the integral of v times u prime times dx. I'm going to denote v prime times dx just as dv. So dv is the product of v prime with dx. And I'm going to denote this as du. Then I'm going to take this formula and I'm going to solve for this term. So I'm going to subtract that from both sides. And what we get is our integration by parts formula. It says, if you want to integrate some function whose derivative you know, that would be the du, times some function whose antiderivative you know, which would be the v, then you will get uv. And then I'm going to move that to the other side. So minus the integral of v du. Instead of writing integration by parts out, I'll just write this. Because everybody who's anybody knows what IBP means, and now you're in the group. Integration by parts. We have a product of two functions, one whose derivative we know easily, which is almost anything, and one whose antiderivative we know easily. We separate them out, find the derivative of u, put it in here, find the antiderivative of v and put it there. And then we put this integral hopefully is something that's now an elementary integral. So this works best on integrals of the form x times the sine of x, x times the cosine of x, x times e to the x. We'll use it on trig functions times e to the x. Maybe I should have written that in the other way,
It would be e to the x sin of x is how you.
right? Products of two functions like that. And it even works well on integrating the natural log of x, the arctangent of x, arcsine of x, arcsecant of x. If they're by themselves or if they're multiplied by another x. Typically a polynomial times a function whose antiderivative we know. Or a function whose derivative we know, but we don't know its antiderivative. That's where we'll use integration by parts. So let's do one of the easiest ones, just the old x sine of x one. I ran some off for you guys. Let me look in here. I ran my examples off. Probably did. I left them in my office. Bummer. No, that's the way I roll. Yeah, I did. I ran off some examples and I just didn't give them to you, so we get to write on the board. And I have wasted paper. I put them in my notebook last time. Look at all the papers I
Because you're
get to
talking
grade.
to- You were talking
So
about.
you
it.
grade all your trading students, like all of their papers?
All of them.
Are they short answer too?
The class with 150, I mixed short answer with multiple choice. But I said I'd give partial credit on the multiple choice if they showed work.
How long did that take?
And most.
Took too long, about 2-3 bottles of
Wait, so
wine.
do you have TAs?
Oh,
Why? You don't.
because then you have to grade what the TAs did. I've tried TAs. TAs are pretty useless, which is sad because that's how I put myself through school as a paper grader.
You were like, oh man, I wasted.
But I was so much
Somebody's time.
smarter than them.
Oh, okay.
Okay, let's integrate x times the sine of x using this technique of integration by parts. So I'm gonna rub this out. So first, pay attention, you just can't integrate the first term as x squared over 2, integrate the second term as minus sine of x, and then multiply those two together and expect to have the right antiderivative. Because remember, we're looking for a function whose derivative is this. So if you do the typical freshman mistake and say that this is equal to x squared over 2 times minus the cosine of x, you're not going to be correct. There is no product of derivatives. And I can show you that you're not going to be correct by taking the derivative of this. Okay, so this is not equal to that because if I were to take the derivative of this, you take the first times the derivative of the second plus the second times the derivative of the first. And do you see any way in heck that that's going to simplify to x sine of x?
No.
Not even close. So it's the product that throws us off. If this were a sum, then we can go term by term. So working backwards from the product rule, we've generated a formula that hopefully will help us compute this integral. So I think of it as being two pieces. The first piece and the second piece is everything else. And the biggest part of, I can integrate both of them. I can integrate x, I can integrate sine of x, but the biggest part I can integrate by itself is that one. So I'm going to call that part dv, sine of x dx. And so that leaves me u is x. So I have a u and a dv. Pick one to be u, pick one to be dv. On the right-hand side, I'm going to need to find the derivative of u, and on the I'm also going to have to find v. I get the derivative of u by taking the derivative of both sides of this, just like we do with an ordinary u du substitution. So here du is going to be dx. This represents the differential in v. So if I integrate both sides here, I'll get my v. So to get to the next line, I am integrating. I'll put this on the board now. I'm going to integrate the dv. I'm going to integrate the sine of x dx. But that step I'll do in my head after this example. So think of this as a 1 times dv. So the integral of 1 with respect to v is what gives me the v. And then the integral of the sine of x is negative cosine of x. So I have the 4 parts that are needed for the formula. I'm gonna put them up here, and I'm gonna write the parts. It's uv minus the integral of v du. So I take my u times my v. In this example, it'll be x times minus cosine of x. I put minus sign out front. Minus the integral of v, which is a minus cosine of x, times du is dx. So these two minus signs look awkward. Let's put them together and put a plus sign in front. So I'll pull it down here. Minus x cosine of x plus the integral of cosine of x dx. And I look at that second integral and think, bam, I can do that one. Integral of cosine of x is?
Sine of x.
And so here's the function who has as its derivative my original integrand. I'll prove it to you by taking the derivative of that. And the claim is the derivative of this gives you that. Derivative of this gives you that. Let's check. Check our answer. Derivative with respect to x of what we just got is our antiderivative. The product rule here, we get the first times the derivative of the second, plus the second times the derivative of the first. Now I'm going to take the derivative of sine of x and get a cosine of x. These two add together to give me 0. Those two multiply together to give me a positive. And there's what we were integrating. So that is indeed the antiderivative. Pretty cool, huh? Yes, sir.
You're always gonna take dv as the second half. of the
No,
equation.
sometimes we'll take it as the first half. Sometimes we'll even have to take some stuff out of here.
How is that determined? Are we gonna find out?
By experience. You always try to look for the largest part of this integral that you know how to integrate. What's the most of that that I can integrate? And that's going to be your dv. What's left will be u because I could take the derivative of almost anything. Right? There's only a limited number of things that I can integrate.
That was scarier at first.
Yeah. Scarier at first. Okay. So here's my next one. Answers your question. X squared times e to the x squared. So I see the biggest part of this is the e thing in it, e to the x squared, but I can't integrate e to the x squared by itself, can I? What would I need?
You need 2x.
I need a 2x. So what I'm going to do is I'm going to borrow one of these x's out here and think of that as x times x e to the x squared. And then I'm going to pick dv to be my x e to the x squared. So I've got to look for the biggest part that I can integrate. So I'm going to write that as x times x e to the x squared dx. Now I can integrate that. It takes a few steps, but I can integrate that. I needed the derivative of this to appear as part of my integrand. So that leaves this part as the du term, or the u term, right? So I pick one of them to be u, and I pick one of them to be the part that I can integrate. I'm going to take u to be x. I'm going to take dv to be x e to the x squared. So this part's quick. Du here is dx. This part here I need to integrate. So I'm gonna put this in red again. I'm gonna integrate 1 times dv. And I'm gonna integrate x e to the x squared dx. This is where I get the v. This is where I need to do a few steps. Usually we would take this part to be u and then it's du, but I've already used a u in my formula. Let's grab another letter from the alphabet. W. Let's let w be this x squared. And dw is 2x dx. So 1/2 dw is x dx. So that x dx is the 1/2 dw. So this integral is going to look like e to the w times 1/2 dw. What's the integral of e to the w?
You love the W.
That does not roll off the tongue.
So we get e to the w here, and w was x squared. So let me go back to black. V is going to be 1/2 e to the x squared. So not always will you be able to do the integral in your head. You might have to find your dv by a little work. But what we need is the u v minus the integral of v du. So let's put it up here. My formula. Put u times v minus the integral of v times du. So u is x, v is 1/2 e to the x squared. So x times 1/2 e to the x squared. Minus the integral of v. V is 1/2 e to the x squared. V du. Du is dx. Uh-oh. Oh, I can't do this integral. I just made an example I can't do.
That's a
Hard,
complete answer.
hard.
No solution.
Well, there is a solution, it's just,
You don't know it yet. Didn't realize that was gonna happen to this.
We got in some practice.
We got it, but you have to realize you don't know how to do this. How do I know I don't know how to do this?
because we don't have another X to.
Because I don't have another x there. Let me just make sure I didn't lose an x. uv minus the integral of v du. uv minus the integral of v du. No, I don't know how to do that one. That's a bummer. I wasted your time. Had I remembered to bring my handout of examples, I wouldn't have pulled that one out of the air. With a mistake on it. Bummer.
How could you fix it?
Should
So
have done it
it's-
as cubed.
just switch it to X cube.
Already done this one.
Yeah, just, play back the recording, cut that part out.
Yeah, yeah, you're gonna have to rewind.
Yeah,
the
I need an
recording a
x
little
cubed
bit.
right there.
Next cubed on which one?
I need this to be x cubed
Okay,
here.
Then it goes x
And then
squared.
I'd have an extra x down here.
Hmm,
And I'd fit the extra x where I needed it with my VDU.
So would you turn it into x squared times x e to the x
Yeah,
squared?
let's do it. What the heck? And I do that. All of that's the same. This is what's going to change, so that's easy to change. This becomes 2x dx. Right? Now I'm gonna fix it over there. Are you with me? I made that x cubed, I borrowed an x as before, but it leaves me an x squared. That helps because when I take the derivative of x squared, I get a 2x dx. I needed that in my du term because eventually I have to multiply v du. I start by multiplying u with v, so I get x squared times 1/2 e to the x squared.
So since that, like the exponent itself is raised to a power, can we not change that to 1/2 e to the 2x, or would that just throw us off?
No, it won't be 1/2 e to the 2x, because I never touched that one.
Okay.
This is the one that I'm working with. Okay, so that's just my u times my v. Now I set up the integral of v times du. So here's my integral. V was 1/2 e to the x squared. Du is 2x dx. I'm going to simplify that in the next line. Let me rewrite that as 1/2 x squared e to the x squared. I'm going to multiply that 2 with that 1/2 and then minus the integral of x e to the x squared dx. And now I can do that integral because I just did it a second ago. I just integrated x e to the x squared and got that. So I'm going to do it now. And that's what we were looking to get. Okay. The point of that one was sometimes you can't just look at it and say one of the terms is u and one's dv. You have to know how to integrate that other part. That you had to know you needed an x.
Random question, but does web work require the plus C?
No.
It does.
You-
Sometimes. It doesn't,
Sometimes,
Only sometimes.
right, the web work comes from a wide variety of sources, so depending on who wrote the code, sometimes they put the plus C in there and sometimes they don't.
It'll tell you, I think, because whenever in like Calc 1, when we were learning it, I
Yeah.
think we did have to put plus C, but it'll tell you, I think.
Yeah, just don't submit immediately. If you like preview answers, it'll say C is not a variable.
How could you forget the plus C? How could you forget that?
It's like the most important part.
All right, here's one for you to try.
Credit for just putting plus C.
That makes sense.
Pick another letter. Hey, yeah.
Yeah.
Okay, x to the 5th times the natural log of x. So you're looking for the most that you can integrate if it were by itself. You picked it out, what's the most that you can integrate out of the x to the 5th natural log of x? The x to the 5th. We know how to take the derivative of a log of x, we just don't know how to integrate. So if you have an integral that has a logarithm, always that's the u. The rest is the dv. Logarithms are automatically the u. So we'll take u to be the natural log of x. dv is the x to the 5th times dx. You need to take the derivative of the u, the antiderivative to get the v. What's the derivative of the natural log of x? 1 over x, and I'm going to put the dx there. All right, I've shown you several times that when you integrate 1 times dv, you get v. So now you're doing the part in your head on the right. What's the integral of x to the 5th dx?
X to the 6 over 6.
Okay. So I've got room down here. You're going to put u times v minus the integral of v du with the hope that in the second iteration, this is an easier integral to do. So u times v, I like to put the polynomial in front of the logarithm. So let me write that as x to the 6th over 6 times the natural log of x. There's my u times v. Minus the integral of v du. Du is 1 over x dx. So look at that second integral and tell me if you know how to integrate it.
You have to
You
just make it
simplify
x to the
it.
5 together.
Yeah, you can go ahead and simplify x to the 6th divided by x is x to the 5th. That 1/6 is a constant, we can pull it out. So that second integral is just 1/6 times the integral of x to the 5th. So make sure you simplify first. Don't just look at that as a product and go, well, I don't know how to do that. That's not a v, that's an x. minus 1/6 times the integral of the natural log, good God. 9 times the integral of x to the 5th dx. So one more step and we've got our answer.
Just, x minus x to the 36, 8x to 6 over 36.
There you go. So we have x to the 6 over 6 times the natural log. I've lost my variable altogether here. Then I got a 1/6. Now I integrate and I get another x to the 6 over 6. That poor lonely plus c on the end. Let everybody know that you're done. Yeah, you can factor it in all kinds of ways.
That might be fun.
I'm just leave it there. See how we did that? Let's do the same problem about the x to the 5th. Do it again. That out. How would you do that one?
Yes, it's a 1, yes.
Same way, right? Take out the x to the 5th. So we have to take u to be the log of x. That leaves dv to be the dx. You take u to be the natural log of x. dv is the dx. And as before, the derivative of u gives us 1 over x dx. And what do I get when I integrate this line? The v is x. So if we use integration by parts on that, we now set up our uv minus the integral of v du. So my uv will be the natural log of x times x. I'll write that in the other order. Minus the integral of v, well, v is going to be x. du is 1 over x dx. So just like before, you get a second integral that when you simplify it first is an easy integral. X times 1 over x is just 1. What do you get when you integrate 1? X. And let everybody know you're done. So you can add that to your list of formulas. You can add that to your list of formulas. The integral of the natural log of x is x ln of x minus x. You do that so many times, eventually, just like with the sine squared, you don't do all those crazy trig reduction formulas, you just spit out the answer. If you want to add it to your list of formulas, here's a new formula. The integral of the natural log of x dx is x ln x minus x plus c. Okay.
Can we use this technique for like any unknown integral that we know the derivative of?
Right,
So we don't even.
like an
So
arctangent.
technically you could just
You
use
could
this
figure it
instead of,
out.
figure this out for everything, do it the long way instead of memorizing all those tables.
Almost. Our hope is that we get an integral that we can do.
But it doesn't always.
Yeah, there are still things where integration by parts won't be the wisest thing to try. Sometimes it'll work with some clever manipulations, but sometimes the clever manipulations aren't worth the effort. There will be other ways to do some products
And how do you know if it's gonna work or not?
by trying it. You do half as many as, if you do, again, experience is the key. Just by trying so many of them, you'll recognize which ones work easier with integration by parts and which ones don't. Polynomial terms multiplied with ease are great candidates for integration by parts. This one's easier than the one we did a minute ago, because I just have e to the x, not e to the x squared. But do you agree that the e to the x is the biggest part you can integrate? So let's pick e to the x dx is the dv, let x to the fourth be the u. We'll take u to be the x to the fourth, dv to be the e to the x dx. du means we're taking the derivative over there, so I get 4x cubed dx. To get the v, we integrate both sides here. Integral of dv is v. What's the integral of e to the x dx?
EDX.
Is d to the x.
I don't remember that one.
You good with me?
I don't remember. Yeah.
uv minus the integral of v du goes up here. Keep writing it down so you'll remember it. So u times v puts an x to the fourth e to the x here, minus the integral of v, 4x cubed, dv, v is e to the x, e to the x times 4x cubed dx. I just wrote it in the wrong order, but I always like to put the polynomial first. uv minus integral of v du. All right, follow the dotted line.
But then to get the integral of that.
How do we get the integral of the other one?
Same thing.
Again.
Product and do
We're
it
gonna
again.
do integration by parts again. Right?
Is it possible to do this infinitely?
Get a high enough.
I'm gonna do this one 4 times. This problem has 4 iterations of integration by parts in it. So be patient.
What do we have, like W and Q?
Now, do you want us to use new variable?
Now, I'm just gonna say that I'm gonna do the second time through. So I'm gonna keep with the same pattern though. My initial u was the polynomial term and my dv was the e term. Keep the pattern. So here u is gonna be 4x cubed and dv is e to the x dx. Take the derivative of the u to get 12x squared times dx. Take the antiderivative here, still the integral of e to the x is e to the x. So v is e to the x. This is part of your antiderivative. Copy it down. X to the fourth, e to the x. Minus. Now that minus sign is going to go in front of my integration by parts scheme. So to make sure I don't lose a sign, I'm going to put brackets here. And inside the brackets, we will put our second iteration of our uv minus the integral of v du. So my uv is 4x cubed e to the x, or minus the integral of v du. So I'll put the 12x squared e to the x dx. And you still have a polynomial times an e to the x. So you're excited you get to do integration by parts again.
It's a pattern.
Really good for
It
practice.
is a pattern. I'm gonna show you how to do this real quick after we're done, because it's an easy pattern. Okay, but before I do integration by parts again, I'm gonna take care of the brackets here, because I don't want to start nesting a bunch of brackets. I take the brackets away and make this minus, make that plus. Okay? X to the fourth, e to the x minus 4x cubed e to the x plus the integral of 12x squared e to the x dx. And here we're going to do integration by parts again.
Wonder if it'll give us 12x squared to the e times e to the x again.
So I'm going to write third time. I need to pick a u and a dv. What's u going to be?
squared.
12x squared. And so that leaves dv to be the e to the x dx. So du is 24x dx. V is e to the x. These two terms are part of my antiderivative, so let's copy them down. Then we're going to replace this integral with uv minus the integral of e du. So we have x to the fourth, e to the x, minus 4x cubed, e to the x, plus. I don't need brackets because of the plus sign. I used brackets last time because I had a minus sign here. So let's go ahead and put our uv minus integral of v du. So using our third iteration, uv is 12x squared times e to the x minus the e to the x times the 24x dx inside the integral sign. So what I just say, uv is 12x squared e to the x minus the integral of v du. I'll have a 24x e to the x dx. The presence of the x right here means another integration by parts. But this will be our last one because its derivative will be a constant. So, fourth time. Stick with the pattern. U was the polynomial term. dv was the e to the x dx. du is 24 dx. v is e to the x. Need more board than what I got. I don't need any of this. I can rub all of this away. Well, I'm going to come out here horizontally. Okay, copy down the first three terms. They're part of the antiderivative. X to the fourth, e to the x, plus 4x cubed, e to the x, plus 12x squared, e to the x, minus. Now I need my integration by parts scheme. The presence of the minus sign makes me put brackets. And here, uv minus the integral of v du. Using our fourth time. So uv is 24x times e to the x. Minus the integral of v du, and that's just going to be 24 e to the x dx. That's a straightforward integral. Okay, so because that's just a constant times e to the x, we'll be done in this next step. So here's your antiderivative. X to the fourth, e to the x, plus 4x cubed, e to the x, plus 12x squared, e to the x. Distribute the minus sign, minus 24x, e to the x. Keep distributing the minus sign, so plus, the integral of 24 e to the x is? 24 e to the x. 24 e to the x. Let everybody know you're done. Maybe you want to check your answer. See if the derivative of this.
I
Gives
think
you-
you should have a minus sign on the second term. I think.
I think
Minus
so.
x
I do. I do. Moving horizontally threw me off.
I'm so proud. I think I got all my signs right. I'm very, very proud of myself.
Very nice.
So these terms here are always just derivatives, right? And these are always antiderivatives. If you know you're going to do multiple integration by parts, you can do this in table form. And I can get all of that I had to erase the board with in one step. Make this table. So here's the table form for repeated integration by parts. The things that would have repeated integration by parts would be x to a power times e to the x, x to a power times the sine of x, x to a power times the cosine of x. Any of those would have to be repeated depending on what the power is. Fourth power, we have 4 iterations of integration by parts. If I had an x to the 10th up there, I'd have to do 10 iterations of integration by parts. But we can put it in table form. We pick a column for u and a column for dv. U is the polynomial part, because we need something whose derivatives will vanish after a certain time. E to the x has an infinite number of derivatives, so I can't pick that as u. U has to be the polynomial term. And that leaves me with e to the x as the dv. Now we're going to take derivatives of x to the 4th until the last derivative is 0. So I'm going to have a 4x cubed, a 12x squared, 24x, 24, and now here's my 0. So we need a row for everything until we get a derivative of 0. And for however many rows we have, we generate antiderivatives over here, which is easy because the integral of e to the x is always e to the x. I'm always integrating the expression right above it. That table has this answer in it somewhere. Can you see where?
And then the signs flip back and forth.
Signs split back and
I
forth.
have a question.
Yes,
Isn't that a
That's so
negative?
nice.
Yeah.
Sure.
It's a negative, look about it.
Oh, it is.
And then do you have alternating negatives? Is that the rule?
In this particular example, you do.
Okay.
Take the diagonal, multiply them together, and then change sign. You always start with plus, minus, plus, minus, plus. That would be minus. But I'm not going to use that one. I take that, x to the 4th, e to the x times plus, minus 4x cubed e to the x, plus 12x squared e to the x, minus 24x e to the x, plus 24 e to the x. The rest of the terms are zeros. If you choose the diagonals, that gives you the integration by parts.
So e to the x squared,
E to the x squared is problematic. We
because
saw
you
that
would
in-
get infinite.
Well, we'd have to have an x e to the x squared over there. Right?
But if you have, well, if it was just purely e to the x squared.
Oh, we don't know how to do that.
You would have an infinite regression using this power.
Well, you couldn't. You can't integrate e to the x squared by itself.
But that's what I'm saying, you'd get an infinite regression based on this.
Even, I don't know where the infinite regression comes in.
Because you would get,
Because you're calling that your u?
yes, you
Yeah.
call e. to
Right,
the
you've
x-
got to have something whose derivatives vanish.
Yes.
You can't use this on things who has a derivative that's non-zero. Yes, sir.
So if our dv had been like cosine of
Hey, let's
x,
do that. In table form, integrate x squared cosine of x. It just takes 2 iterations of integration by parts, but do it in table form. The integral of x squared e to the cosine of x. Integral of x squared times cosine of x.
On our dv side, are we taking the derivative or the antiderivative?
On the dv side, we take the antiderivative. We're going to integrate x squared times the cosine of x. I'm going to let you do it in table form. I'm going to do it by integration by parts twice, and we're going to see if we get the same answer.
For table form is the first one in the second column.
Cosine of x. dv is cosine of x.
Okay, since ours.
And then you got to integrate cosine of x. So you're going to do it that way. You're going to take u and dv, x squared here, cosine of x there. Make however many rows you need until you get a derivative that vanishes. And multiply the diagonals and alternate the signs.
You always start with the positive unless there's good reason.
You always start with positive. Plus minus, plus minus, plus minus, down the diagonal. Think you got it? Okay, so I'm gonna take derivatives here until I run out of them. I get a 2x, then a 2, and then I'm done. Tiny table. Now I gotta integrate cosine. The integral of cosine is the sine. Integral sine is minus the cosine. So integral minus cosine is minus sine. Agreed? Now I'm going diagonally. That, plus, minus, plus. So I'm gonna have a positive x squared sine of x minus 2x times the negative cosine of x. And then plus 2 times the negative sine of x.
The second term should be positive, I think.
It really, when I put those together, I'm gonna kind of just exaggerate. And so I have a 0 next, so I put my plus c there. So now I'm gonna put the signs together. So your final answer is x squared sine of x plus 2x cosine of x minus 2 sine of x. Okay? But I'm gonna pretend we don't know the table, and I'm gonna go ahead and integrate my parts twice. So without the table. I'm gonna integrate x squared cosine of x dx. Even the table doesn't save the ink for me. I'm gonna take u to be the x squared and dv to be the cosine of x dx. So du is 2x dx. Integral of cosine is a positive sign. So now we do uv minus the integral of v du. Right over here, uv is x squared sine of x minus v du. We put it in the integral sign as 2x sine of x dx. Okay, and I've already warned you that a polynomial times a trig is integration by parts, so we do it again. Using the same structure. U is 2x, dv is the sine of x dx. Take the derivative here to get 2 times dx. Take the antiderivative here to get negative cosine of x. So I'm going to pull it up here. First part of my antiderivative has to be copied down again. And this minus sign with brackets. So in here, I put my uv minus the integral of v du. So uv is a negative 2x cosine x minus v du is a negative 2 times the cosine of x dx. So I can see now I just have the constant times the cosine. I can integrate that. I'm going to start putting all these signs together. Plus 2x cosine of x minus gives me a minus here, right? Minus. Then the 2 And the integral of cosine? Positive sine.
You scared the
And-
hell out of about 64.
Right, we got the same thing. Agree? You got to do the fun part. Got something in my eye.
Really, you want to end on,
You want to end on that one?
I gotta kind of pee.
I got much more entertaining ones for you.
So would you say infinity is positive, or infinity is even or odd?
Would you say that infinity is an imaginary
It's
number?
divisible by 2, it's even.
Okay, so then the integral of e to the x squared would be 0. No, 0.
I can show you.
Okay, here's the entertainment.
According to this, at least.
Almost one. You really don't want me to do another one. What if I shut the door and stood in front of it and said you can't go?
Can't do that.
You can always do another one. Some of us will just leave.
Okay, I will put some problems for you. There's a couple of problems with some quirks. I didn't get to see any of the quirks, so I have to do that for you on Monday. So you're gonna have a quirkless weekend. That's good.
This is why I come to that. I'm sure my logic is breaking.
They can't even like support that. That's why Darby's like. But the tables are not. Like the opposite. I think. it's real.
So would that mean it was 0?
It's not zero.
Oh,
That doesn't make any sense.
what?
Why did I say?
I have a question about web work for Sept1. For the write-ups, you have to do 14, but there is no 14.
I'll have to fix that. Maybe you just make your own 14. I'll fix that right now. I just copied and pasted from last semester, but I didn't copy and paste the homework. I made new homework. You have your test. You came in late. You came in late. What you wanted, that's not what you wanted.
I realize I've never turned in my.
Okay, which is okay, because I've never graded 6.3 yet. So let me add it to my stuff to grade.
Well, I just had a few questions.
Oh, yes, sir.
Yeah, so I'm confused about this graph. I don't know if you have to graph it or not, but I just,
Okay.
so,
Have a good
got-
weekend. I sent you an
Thank you.
email, but I don't know if you got it.
Oh, so now I get to grade it twice.
No. I mean.
Well, yeah, because I won't check which papers I have and which emails I have, so I'll grade it twice. I hope you get the same grade on both times I grade it.
Oh, it's just a photo of that,
Oh,
so.
okay.
Thank you.
I mean, there's still a possibility.
I did grade it somebody's test twice. One I had a paper copy because I downloaded it so I could grade it at home, and one I just graded online. And there was a 9-point difference in the way I graded their test. Okay,
Okay, so, just these
All right.
three points here that kind of have me confused.
okay,
So,
4 pi over 3, cosine of 4 pi over 3. 4 pi over 3 is third quadrant, so those are gonna be negative numbers, right? So that's gonna be a -1/2, so that's a -3/2. So 8/2 minus 3/2 is 5/2, which is what you got there. Those are
Yeah.
okay.
so then, if this is 2.5 inch, then that'd be like up here.
No, it's on that ray. You go out 2.5 units on that ray. On 2 pi thirds, that's 2.5. So on the 4 pi thirds, you go out 2.5.
Okay,
The ray itself that forms that angle acts as your x-axis where
okay,
you're going out.
all right, okay then. I had a feeling I was just. unsure. And then there's this, admittedly, I remember I did do this problem,
Mhm.
and I did there, I have now, but I
Okay,
forgot how
so here we go. Let
squaring
me.
this would go.
It's gonna stay at 2 theta. You never square the angle, you just square the trig function.
Okay.
Then we're gonna do UD, the 4 is gonna come out front. And we're gonna take U to be the 2 theta. So du is gonna be 2 times d theta. And I pull the 2 over here and put it with the du.
Okay,
So I get this 1/2 here, that 4, and that 1/2. And this becomes the integral of the sine squared of u. That okay?
yeah,
Then we had a formula for this one. That becomes u over 2 minus the sine of 2u over 4.
Okay,
I'll put these numbers together and just get a 1. So the next step is to put the 2 theta back in there. So we have 2 theta over 2 minus the sine of 2 times 2 theta over 4, and then you put the numbers in.
shouldn't it be, I already
Plus.
printed
Yeah, and so the 2's cancel here. Nothing cancels here, but if you multiply 4 times pi over 4, you get pi. Sine of pi and the sine of negative pi are both 0.
that, okay,
So you're just gonna have pi over 4 minus a negative pi over 4, which is 2 pi over 4 or pi halves. And that's what that 1.57 is.
okay.
Same deal here. You've got a formula for cosine squared. The integral of cosine squared of theta is theta over 2 plus sine of 2 theta over 4. You didn't need a u because you just have a single variable, so go ahead and use a theta. Then in front of that, you got the 16. Not yet, you gotta integrate the 4. A long recording.